Learning objectives. In this chapter, the user would learn the following in detail. Introduction to Object Definition Language, that is called ODL. Class declarations. Attributes in ODL. Relationships in ODL. Inverse relationships. Multiplicity of relationships. Methods and types in ODL. Additional ODL concepts. Multi-way relationships in ODL. Subclasses in ODL. Multiple inheritance in ODL. Extents. Declaring keys in ODL. From ODL to relational designs. Object relational model. From relations to object relations. Nested relations. References. Object-oriented versus object relational. From ODL introduction to OQL. Features of OQL. Additional forms of OQL expressions. Object assignment and creation in OQL. User-defined types in SQL. Operations on object relational data. Ordering relationships on OODTS. Introduction to Object Definition Language ODL. Object Definition Language ODL. Object Definition Language is a text-based language for specifying the structure of databases in object-oriented terms. Like UML, the class is the central concept in ODL. Classes in ODL have a name, attributes, and methods just as UML classes do. Relationships which are analogous to UML's associations are not an independent concept in ODL, but are embedded within classes as an additional family of properties. Class declaration. A declaration of a class in ODL in its simplest form is, that is, the keyword class is followed by the name of the class and a bracketed list of properties. A property can be attribute, a relationship, or a method. Attributes in ODL. The simplest kind of property is the attribute. In ODL, attributes need not be of simple types, such as integers and strings. ODL is a type system that allows us to form structured types and collection types, etc. sets. For example, an attribute address might have a structured type with fields for the street, city, and zip code. An attribute phones might have a set of strings as its type, and even more complex types are possible. An attribute is represented in the declaration for its class by the keyword attribute, the type of the attribute, and the name of the attribute. Example 1. Above figure is an ODL declaration of the class of movies. It is not a complete declaration. We shall add more to it later. Line 1 declares movie to be a class. Following line 1 are the declarations of 4 attributes that all movie objects will have. Lines 2, 3 and 4 declare 3 attributes: title, year, length. The first of these is of character string type and the other 2 are integers. Line 5 declares attributes genre to be of enumerated type. The name of the enumeration list of symbolic constants is genres, and the 4 values the attribute genre is allowed to take are drama, comedy, sci-fi and teen. An enumeration must have a name which can be used to refer to the same type anywhere. Example 2. In example, all the attributes have primitive types. Here is an example with a complex type. We can define the class star by line 2 specifies an attribute name of the star, that is a string. Line 3 specifies another attribute address. This attribute has a type, that is a record structure. The name of this structure is address. and the type consists of two fields, street and city. Both fields are strings. In general, one can define record structure types in ODL by the keyword structure and curly braces around the list of field names and their types. Like enumerations, structure types must have a name which can be used elsewhere to refer to the same structure type. Relationships in ODL. An ODL relationship is declared inside a class declaration by the keyword relationship, a type and the name of the relationship. The type of relationship describes what a single object of the class is connected to by the relationship. Typically, this type is either another class if the relationship is many one, or a collection type if the relationship is one many or many many. Example 3. Suppose we want to add to the declaration of the movie class from example a property that is a set of stars. More precisely, we want each movie object to connect the set of star objects that are its stars. The best way to represent this connection between the movie and star classes is with the relationship. We may represent this relationship by a line. Inverse relationship. Just as we might like to access the stars of a given movie, we might like to know the movies in which a given star acted. To get this information into star objects, we can add the line to the declaration of class star in example. However, this line and a similar declaration for movie omits a very important aspect of the relationship between movies and stars. We expect if a star S is in the stars set for movie M, then movie M is in the starred in set for star S. We indicate this connection between the relationships stars and starred in by placing in each of the declarations the keyword inverse and the name of the word relationship. In the other relationship is in some other class as it usually is, then we refer to that relationship by its scope name, the name of its class followed by a double colon and the name of the relationship. Example 4. To define the relationship starred in of class star to be the inverse of the relationship stars in class movie, we revise the declarations of these classes. Line 6 shows the declaration of relationship stars of movies and says that its inverse is star double colon starred in. Since relationship starred in is defined in another class, its scope name must be used. Similarly, relationship starred in is declared in line 11. Inverse is declared by that line to be stars of class movie, as it must be, because inverses always are linked in pairs. As a general rule, if a relationship R for class C associates with the object X of class C with the object Y1, Y2, etc. Yn of class D, then the inverse relationship of R associates with each of the Y1s, the object X perhaps along with other objects. Multiplicity of relationships. Like the binary relationships of the E given R model, a pair of inverse relationships in ODL can be classified as either many to many, many to one in either direction, or one to one. If we have a many to many relationship between class C and D, then in class C the type of the relationship is set Z, and in class D the type is set C. If the relationship is many to one from C to D, then the type of relationship in C is just D, while the type of the relationship is D is set C. If the relationship is many one from D to C, then the roles of C and D are reversed in 2 above. If the relationship is 1 to 1, then the type of relationship in C is just D, and in D it is just C. Note that as in the E given R model, we allow a many to one or 1 to 1 relationship to include the case where for some objects the 1 is actually none. For instance, a many-to-one relationship from C to D might have a null value of the relationship in some of the C objects. Of course, since a D object could be associated with any set of C objects, it is also permissible for that set to be empty for some D objects. Some ODL classes and the relationship. Example 5. We have the declaration of three classes: movie, star and studio. The first two of these I have already introduced in examples 1 and 2. We also discussed the relationship pair stars and starred in. Since each of their types uses set, we see that this pair represents a many-to-many relationship between star and movie. Studio objects have attributes, name and address. These appear in lines 13 and 14. We have used the same type for addresses of studios as we defined in class star for addresses of stars. In line 7, we see a relationship owned by from movies to studios, and the inverse of this relationship is owns on line 15. Since the type of owned by is studio while the type of owns is set movie, we see that this pair of inverse relationships is many to one from movie to studio. Method and type in ODL. ODL offers the database designer a type system similar to that found in C or other conventional programming languages. A type system is built from a basis of type that are defined by themselves and certain recursive rules whereby complex types are built from similar types. In ODL, the basis consists of primitive types, integer, float, character, character string, boolean and enumerations. The later are list of symbolic names such as drama in line, class names such as movie or star, which represent types that are actually structures with components for each of the attributes and relationships of that class. These types are combined into structured types using the following type constructors. Set. If T is any type, then set T denotes the type whose values are finite sets of elements of type T. Examples using the set type constructor occur in lines 6, 11 and 15. Bag. If T is any type, then bag T denotes the type whose values are finite bags or multi-sets of elements of type T. List. If T is any type, then list T denotes the type whose values are finite list of 0 or more elements of type T. Array. If T is a type and I is an integer, then array T, I denotes the type whose elements are arrays of I elements of type T. For example, array character, 10 denotes character strings of length 10. Dictionary. If T and S are types, then dictionary T, S denotes a type whose values are finite sets of pairs. Each pair consists of a value of the key type T and a value of the range type S. The dictionary may not contain two pairs with the same key value. Structures. If T1, T2, etc. Tn are types and F1, F2, etc. Fn are names of fields, then denotes the type named n, whose elements are structures with n fields. The starth field is named Ft and has type T star. For example, line 10 showed a structure type named address with two fields. Both fields are of type string and have names street and city respectively. The first five types, set, bag, list, array and dictionary, are called collection types. These are different rules about which types may be associated with attributes and which with relationships. The type of relationship is either a class type or a single use of a collection type constructor applied to a class type. The type of an attribute is built starting with the primitive type or types. We may then apply the structure and a collection type constructors as we wish as many times as we wish. Example 6. Some of the possible types of attributes are: number 1, integer; number 2, structure n, string, field 1, integer field 2; number 3, list real; number 4, array, structure n, string field 1, integer field 2, 10. Example 1 is a primitive type, 2 is a structure of primitive types, 3 a collection of primitive type, and 4 a collection of structures built from primitive types. Now suppose the class names movie and star are available primitive types, then we may construct relationship types such as movie or bag star. However, the following are illegal as relationship types. Number 1, structure n, movie field 1, star field 2. Relationship types cannot involve structures. Number 2, set integer. Relationship types cannot involve primitive types. Number 3, set array star 10. Relationship types cannot involve two applications of collection type. Additional ODL concepts, subclasses in ODL. We can declare one class C to be a subclass of another class D. To do so, follow the name C in its declaration with the keyword extends and the name D. Then class C inherits all the properties of D and may have additional properties of its own. Example: we can create a subclass cartoon for movie with the ODL declaration. Declare a class of murder mysteries with the additional attribute weapon. Sometimes, as in the case of a movie like Roger Rabbit, we need a class that is a subclass of two or more other classes at the same time. In ODL, we may follow the keyword extends by several classes separated by colons. Thus, we may declare a fourth class by. Note that when there is a multiple inheritance, there is the potential for a class to inherit two properties with the same name. The way such conflicts are resolved is implementation dependent. Declaring keys in ODL. The declaration of a key or keys for a class is optional. The reason is that ODL, being object-oriented, assumes that all objects have an object identity. In ODL, we may declare one or more attributes to be a key for a class by using the keyword or keys followed by the attribute or attributes forming keys. If there is more than one attribute in a key, the list of attributes must be surrounded by parentheses. The key declaration itself appears inside parentheses following the name of the class itself in the first line of its declaration. Example: to declare that the set of two attributes title and year form a key for class movie, we could have used keys in place of key even though only one key is declared. It is possible that several sets of attributes are keys. If so, then following the word keys, we may place several keys separated by commas. A key that consists of more than one attribute must have parentheses around the list of its attributes, so we can disambiguate a key of several attributes from several keys of one attribute each. The ODL standard also allows properties other than attributes to appear in keys. There is no fundamental problem with a method or relationship being declared a key or part of a key, since keys are advisory statements that the database management system can take advantage of or not, as it wishes. For instance, one could declare a method to be a key, meaning that on distinct objects of the class, the method is guaranteed to return distinct values. When we allow many-to-one relationships to appear in key declarations, we can get an effect similar to that of weak entity sets in the E-given-OR model. We can declare that the object OI referred to by an object O2 on the many sides of the relationship, perhaps together with the other properties of O2 that are included in the key, is unique for different objects OI. However, we should remember that there is no requirement that classes have keys. We are never obliged to handle in some special way classes that lack attributes of their own to form a key, as we did for weak entity set. Example 8. A ODL declaration for cruise. What is this key declaration asserts is that there cannot be two crews that both have the same value for the number attribute and are related to the same audio by unit of. From ODL to relational designs. ODL was actually intended as the data definition part of a language standard for object-oriented database management systems analogous to the SQL create table statement. Indeed, there have been some attempts to implement such a system. However, it is also possible to see ODL as a text-based high-level design notation from which we eventually derive a relational database schema. Thus, in this section, we shall consider how to convert ODL designs into relational designs. Classes become relations and relationships become relations that connect the key attributes of the classes involved in the relationship. Problems in ODL. Number 1. Entity sets must have keys, but there is no such guarantee for ODL classes. Number 2. While attributes in E given are UML and the relational model are of primitive type, there is no such constraint for ODL attributes. From ODL classes to relations. As a starting point, let us assume that our goal is to have one relation for each class and for that relation to have one attribute for each property. We shall see many ways in which this approach must be modified, but for the moment, let us consider the simplest possible case where we can indeed convert classes to relations and properties to attributes. The restrictions we assume are: Number 1. All properties of the class are attributes, not relationships or methods. Number 2. The types of the attributes are primitive, not structures or sets. In this case, the ODL class looks almost like an entity set or a UML class. Although there might be no key for the ODL class, ODL assumes object identity. We can create an artificial attribute to represent the object identity or serve as a key for the relation. Example 9. Figure an ODL description of movie executive. No key is listed, and we do not assume that name uniquely determines a movie executive, unlike stars who will make sure their chosen name is unique. We create a relation with the same name as the class. The relation has 4 attributes, one for each attribute of the class and one for the object identity. We can use certain as the key attribute representing the object identity. Complex attributes in classes. Even when a class properties are all attributes, we may have some difficulty converting the class to a relation. The reason is that attributes in ODL can have complex types such as structures, set, bags, or lists. On the other hand, a fundamental principle of the relational model is that the relation's attributes have a primitive type, such as numbers and strings. Thus, we must find complex attribute types as relations. Record structures whose fields are themselves primitive are the easiest to handle. We simply expand the structure definition, making one attribute of the relation for each field of the structure, class with a structure attribute. Example: Figure 4 is a declaration of class star with only attributes as properties. The attribute name is of primitive type, but attribute address is a structure with 2 fields, star and city. We represent this class by the relation. The key is name, and the attributes street and city represent the structure address, representing set valued attributes. However, a record structures are not the most complex kind of attribute that can appear in ODL class definitions. Values can also be built using type constructors, set, bag, list, array, and dictionary. Each presents its own problems when migrating to the relational model. One approach to representing a set of values for each attribute A is to make one tuple for each value. The tuple includes the appropriate values for all the other attributes besides A. This approach works although it is likely to produce unnormalized relations. Example: stars with a set of addresses and a birth date. Figure shows a new definition of the class star in which we have allowed stars to have a set of addresses and also added a non-key primitive attribute birth date. The birth date attribute can be an attribute of the star relation whose schema now becomes, although name is a key for the class star, our need to have several tuples for one star to represent all the other addresses means that name is not a key for the relation star. In fact, the key for that relation is name, street, city. Thus, the functional dependency name birth date is a BCNF violation, and the multi-value dependency name street city is a 4NF violation as well. There are several options regarding how to handle set-valued attributes that appear in a class declaration along with other attributes, set-valued or not. One approach is to separate out each of set-valued attribute as if it were a many-to-many relationship between the objects of the class and the values that appear in the sets. An alternative approach is to place all attributes, set-valued or not, in the schema for the relation, then use the normalization techniques to eliminate the resulting BCNF and 4NF violations. Notice that any set-valued attribute in conjunction with any single-valued attribute leads to a BNCF violation. Two set-valued attributes in the same class declaration will lead to a 4NF violation, even if there are no single-valued attributes. Representing other type constructors besides record structures and sets, an ODL class definition could use bag, list, array, or dictionary to construct values. To represent a bag, multi-set, which is a single object, can be a member of the bag n times. We cannot simply introduce into a relation n identical tuples. Instead, we could add to the relation schema another attribute count representing the number of times that each element is a member of the bag. A list of addresses could be represented by a new attribute position indicating the position in the list. A fixed length array of addresses could be represented by attributes for each position in the array. Finally, a dictionary could be represented as a set, but with attributes for both the key value and range value, components of the pairs that are members of the dictionary. Of course, attribute types in ODL may involve more than one type constructor. If a type is any collection type besides dictionary applied to a structure, example, a set of structures, then we may apply the techniques as if the structure were an atomic value and then replace a single attribute representing the atomic value by several attributes, one for each field of the structure. This strategy was used in the examples above, where the address is a structure. There are many reasons to limit the complexity of attribute types to an optional structure followed by an optional collection type. Representing ODL relationships. Usually, an ODL class definition will contain relationships to other ODL classes. As in the E-given-R model, we can create for each relationship a new relation that connects the key of the two related classes. However, in ODL, relationships come in inverse pairs, and we must create only one relation for each pair. Many to one, we have an option to combine it with the relation that is constructed for the class on the many side. Doing so has the effect of combining two relations that have a common key. If therefore does not cause a BCNF violation and is a legitimate and a commonly followed option. Object relational model. The relational model and the object-oriented model, type feed by ODL, are two important points in a spectrum of options that could underlie a database management system. For an extended period, the relational model was dominant in the commercial database management system world. Object-oriented database management systems made limited inroads during the 1990s but never succeeded in winning significant market share from the vendors of relational database management systems. Rather, the vendors of relational systems have moved to incorporate many of the ideas found in ODL or other object-oriented database proposals. As a result, many database management system products that used to be called relational are now called object relational. This section extends the abstract relational model to incorporate several important object relational ideas. From relations to object relations. While the relation remains the fundamental concept, the relational model has been extended to the object relational model by incorporation of features such as: number 1. Structured types for attributes. In that, instead of allowing only atomic types for attributes, object relational systems support a type system like ODL's types built from atomic types and type constructors for structures, sets, and bags, for instance. Especially important is a type that is a bag of structures, which is essentially a relation. That is, a value of one component of a tuple can be an entire relation called a nested relation. Number 2. Methods. These are similar to methods in ODL or any object-oriented programming system. Number 3. Identifiers for tupules. In object relational systems, tupules play the role of objects. It therefore becomes useful in some situations for each tuple to have a unique ID that distinguishes it from other tuples, even from tuples that have the same values in all components. This ID, like the object identifier assumed in ODL, is generally invisible to the user, although there are even some circumstances where users can see the identifier for a tuple in an object relational system. Number 4. References. While a pure relational model has no notion of references or pointers to tuples, object relational systems can use these references in various ways. Nested relations. Nested relations. In the nested relational model, we allow attributes of relations to have a type that is not atomic. In particular, a type can be a relation schema. As a result, there is a convenient recursive definition of the types of attributes and the types schemas of relations. Basis. An atomic type, integer, real, string, etc. can be the type of an attribute. Induction. A relation's type can be any schema consisting of names for one or more attributes and any legal type for each attribute. In addition, a schema also can be the type of any attribute. An attribute that is a schema will be represented by the attribute name and a parenthesized list of the attributes of its schema. Since those attributes may themselves have structure, parentheses can be nested to any depth. Example: let us design a nested relation schema for stars that incorporates within the relation an attribute movies, which will be a relation representing all the movies in which the star has appeared. The relation schema for attribute movies will include the title, year, and length of the movie. The relation schema for the relation stars will include the name, address, and birth date, as well as the information found in movies. Additionally, this address attribute will have a relation type with attributes street and city. We can record in this relation several addresses for the star. The schema for stars can be written. An example of a possible relation for nested relation stars, we see in the relation two tupules, one for Carrie Fisher and one for Mark Hamill. The values of components are abbreviated to conserve space, and the dashed lines separating tuples are only for convenience and have no notational significance. A nested relation for stars and their movies. In the Carrie Fisher tuple, we see her name and atomic value followed by a relation for the value of the address component. That relation has two attributes, street and city, and that there are two tuples corresponding to her two houses. Next comes the birth date, another atomic value. Finally, there is a component for the movie's attribute. This attribute has a relation schema as its type, with the components for the title, year, and length of a movie. The relation for the movie's component of the Carrie Fisher tuple has tuples for her three best known movies. Mark Hamill has the same components. His relation for address has only one tuple because in our imaginary data has only one house. His relation for movies looks just like Carrie Fisher's because their best known movie happened by coincidence to be the same. Note that these two relations are two different tuple components. These components happen to be identical, just like two components that happened to have the same integer value. Example 124. References. The fact that movies like Star Wars will appear in several relations that are values of the movie's attribute in the nested relation. Stars is a cause of redundancy. In effect, the schema has the nested relation analog of not being in BCNF. However, decomposing the stars relation will not eliminate the redundancy. Rather, we need to arrange that among all the tuples of all the movies relations, a movie appear only once. To cure the problem, object relations need the ability for one tuple T to refer to another tuple S rather than incorporating S directly in T. We thus add to our model an additional inductive rule. The type of an attribute also can be a reference to a tuple with a given schema or a set of references to tuples with a given schema. If an attribute A has a type that is a reference to a single tuple with a relation schema named R, we show the attribute A in a schema as A star R. Notice that the situation is analogous to an ODL relationship A whose type is R, that is, it connects to a single object of type R. Similarly, if an attribute A has a type that is a set of references to tuples of schema R, then A will be shown in a schema as A. This situation resembles an ODL relationship A that has type set I. Sets of references as the value of an attribute. Example, an appropriate way to fix the redundancy is to use two relations, one for stars and one for movies. In this example only, we shall use a relation called movies, that is an ordinary relation with the same schema as the attribute movies in example. A new relation stars that has a schema similar to the nested relation stars of that example, but the movies attribute will have a type that is a set of references to movies tuples. The schemas of the two relations are thus the data of figure converted to this new schema. Notice that because each movie has only one tuple, although it can have many references, we have eliminated the redundancy inherent in the schema of example. Object-oriented versus object relational. Object-oriented versus object relational. The object-oriented data model as typified by ODL and the object relational model discussed here are remarkably similar. Some of the smallest points of comparison follow. Objects and tuples. An object's value is really a structure with components for its attributes and relationships. It is not specified in the ODL standard how relationships are to be represented, but we may assume that an object is connected to related objects by some collection of references. A tuple is likewise a structure, but in the conventional relational model, it has components for only the attributes. Relationships would be represented by tuples in another relation. However, the object relational model, by allowing sets of references to be a component of tuples, also follows relationships to be incorporated directly into the tuples that represent an object or entity. Methods. The SQL 99 standard and all implementations of object relational ideas allow the same ability as ODL to declare and define methods associated with any class or type. Type systems. The type systems of the object-oriented and object relational models are quite similar. Each is based on atomic types and construction of new types by structure and collection type constructors. The choice of collection types may vary, but all variants include at least sets and bags. Moreover, the set or bag of structures type plays a special role in both models. It is the type of classes in ODL and the type of relations in the object relational model. References and object IDs. A pure object-oriented model uses object IDs that are completely hidden from the user and thus cannot be seen or queried. The object relational model allows references to be part of a type, and thus it is possible under some circumstances for the user to see their values and even remember them for future use. Backwards compatibility. With little difference in essential features of the two models, it is interesting to consider why object relational systems have dominated the pure object-oriented systems in the marketplace. As relational database management systems evolved into object relational database management systems, the vendors were careful to maintain backwards compatibility. That is, newer versions of the system would still run the old code and accept the same schemas should the user not care to adopt any of the object-oriented features. On the other hand, migration to a pure object-oriented database management system would require the installations to rewrite and reorganize extensively. Thus, whatever competitive advantage could be argued for object-oriented database systems was insufficient to motivate many to make the switch. Operations on object relational data. All appropriate SQL operations from previous chapters apply to tables that are declared with a UDT or that have attributes whose type is a UDT. There are also some entirely new operations we can use, such as reference following. However, some familiar operations, especially those that access or modify columns whose type is a UDT, involve new syntax. Following reference. Suppose A is a value of type reference T, then X refers to some tuple T of type T. We can obtain tuple T itself or components of T by two means. Number 1. Operator tends to has essentially the same meaning as this operator doesn't see. That is, if X is a reference to a tuple T and A is an attribute of T, then X tends to A is a value of the attribute A in tuple T. Number 2. The dereference operator applies to a reference and produces the tuple referenced. Example. In line 3, the expression star tends to name produces the value of the name component of the movie star tuple referred to by the star component of any given stars in tuple. Thus, the var class identifies those stars in tuples whose star components are references to the Brad Pitt movie star tuple. Line 1 then produces the movie tuple referred to by the movie component of those tuples. All three attributes title, year and genre will appear in the printed result. Accessing components of tuples with the UDT. When we define a relation to have a UDT, the tuples must be thought of a single object rather than list with the components corresponding to the attributes of the UDT. As a case in point, consider the relation movies declared. This relation from UDT movie type which has three attributes: title, year and genre. However, a tuple T in movies has only one component, not three. That component is the object itself. If we drill down into the object, we can extract the values of the three attributes in the type movie type as well as use any methods defined for the type. However, we have to access these attributes properly since they are not attributes of the tuple itself. Rather, every UDT has an implicitly defined observer method for each attribute of that UDT. The name of the observer method for an attribute X is X. We apply this method as we would any other method for this UDT. We attach it with a dot to an expression that evaluates to an object of this type. Thus, if T is a variable whose value is of type T and A is an attribute of T, then T dot X is the value of X in the tuple object denoted by T. In practice, object relational database management systems do not use method syntax to extract an attribute from an object. Rather, the parentheses are dropped and we shall do so in what follows. Example: the tuple variable M is still necessary, however. The dot operator can be used to apply methods as well as to find attribute values within objects. These methods should have the parentheses attached even if they take no arguments. The generator and mutator functions. In order to create a data that conforms to a UDT or to change components of objects with a UDT, we can use two kinds of methods that are created automatically along with the observer methods whenever a UDT is defined. These are: number 1, a generator method. This method has the name of the type and no argument. It may be invoked without being applied to any object, that is, if T is a UDT, then T returns an object of type T with no values in its various components. Number 2, mutator methods. For each attribute X of UDT T, there is a mutator method X of V. When applied to an object of type T, it changes the X attribute of that object to a value V. Notice that the mutator and observer method for an attribute each have the name of the attribute but differ in that the mutator has an argument. Example: lines 2 through 4 introduce the arguments S, C and N, which will provide values for a street, city and a star name respectively. Lines 5 and 6 declare two local variables, each is of one of the UDTs involved in the type for objects that exist in the relation movie star. At lines 7 and 8, we create empty objects of each of these two types. Lines 9 and 10 put real values in the object new address. These values are taken from the procedure arguments that provide a street and a city. Line 11 similarly installs the argument N as the value of the name component in the object new star. Then line 12 takes the entire new address object and make it the value of the address component in new star. Finally, line 13 inserts the constructed object into relation movie star. To insert a star into movie star, we can call procedure insert star. It is much simpler to insert objects into a relation with a UDT if your database management system provides a generator function that takes values for the attributes of the UDT and returns a suitable object. For example, if we have functions address type S, C and star type N, A that return objects of the indicated types, that we can make the insertion at the end of example with an insert statement of a familiar form. Ordering relationships on UDTs. Objects that are of some UDT are inherently abstract in the sense that there is no way to compare two objects of the same UDT, either to test whether they are equal or whether one is less than another. Even two objects that have all components identical will not be considered equal unless we tell the system to regard them as equal. Similarly, there is no obvious way to sort the tuples of a relation that has a UDT unless we define a function that tells which of two objects of that UDT precedes the other. Yet, there are many SQL operations that require either an equality test or both an equality and a less than test. For instance, we cannot eliminate duplicates if we can't tell whether two tuples are equal. We cannot group by an attribute whose type is a UDT unless there is an equality test for that UDT. We cannot use an order by class or a comparison like less than in a var class unless we can compare two elements. To specify an ordering or comparison, SQL allows us to issue a create ordering statement for any UDT. There are a number of forms of this statement may take, and we shall only consider the two simplest options. Number 1. The statement says that two members of UDT T are considered equal if all of their corresponding components are equal. There is no less than defined on objects of UDT T. Number 2. The following statement says that any of the 6 comparisons less than or equal to, greater than or equal to, and may be performed on objects of UDT T. To compare objects x1 and x2, we apply the function f to these objects. This function must be written so that f of x1, x2 less than 0. Whenever we want to conclude that x1 less than x2, f of x1, x2 equal to 0 means that x1 equal to x2, and f of x1, x2 greater than 0 means that x1 greater than x2. If we replace ordering full with equals only, then f of x1, x2 equal to 0 indicates that x1 equal to x2, while another value of f of x1, x2 means that x1 not equal to x2. Comparison by less than is impossible in this case. Example, let us consider a possible ordering on the UDT star type. If we want only an equality on objects of this UDT, we could declare that statement says that two objects of star type are equal if and only if the names are equal as character strings and their addresses are equal as objects of UDT address type. The problem is that unless we define an ordering for address type, an object of the type is not even equal to itself. Thus, we also need to create at least an equality test for address type. A simple way to do so is to declare that two address type objects are equal if and only if their streets and cities are each equal as strings. We could do so by alternatively, we could define a complete ordering of address type objects. One reasonable ordering is to order addresses first by cities alphabetically and among addresses in the same city by street address alphabetically. To do so, we have to define a function, say address leg, that takes two address type arguments and returns a negative 0 or positive value to indicate that the first is less than, equal to, or greater than the second. We declare. Notice that if we reach line 7, it must be that the two city components are the same, so we compare the street components. Likewise, if we reach line 9, the only remaining possibility is that the cities are the same and the first street precedes the second alphabetically. In practice, commercial database management systems each have their own way of allowing the user to define comparisons for a UDT in addition to the two approaches mentioned above. Some of the capabilities offered are Subdivision A. Strict object equality. Two objects are equal if and only if they are the same object. Subdivision B. Method defined equality. A function is applied to two objects and returns true or false, depending on whether or not the two objects should be considered equal. Subdivision C. Method defined mapping. A function is applied to one object and returns a real number. Objects are compared by comparing the real numbers returned. User defined types in SQL. The central extension turns the relational model into the object relational model. In SQL is the user defined type or UDT. We find UDTs used in two distinct ways. Number 1. A UDT can be the type of a table. Number 2. A UDT can be the type of an attribute belonging to some table. Defining types in SQL. The SQL 99 standard allows the programmer to define UDTs in several ways. The simplest is as a remaining of an existing type. Renames a primitive type such as integer. Its purpose is to prevent error caused by accidental coercions among values that logically should not be compared or interchanged even though they have the same primitive data type. Example. In our running movies example, there are several attributes of type integer. These include length of movies, cert hash of movie XC, and press C hash of studio. It makes sense to compare a value of cert hash with the value of press C hash, and we could even take a value from one of these two attributes and store it in a tuple as the value of the other attribute. However, it would not make sense to contribute a movie length with the certificate number of a movie executive, or to take a length value from a movie's tuple and store it in the cert hash attribute of a movie exe tuple. If we create types, then we can declare cert hash and press C hash to be of type cert type instead of integer in the respective relation declarations, and we can derive length to be of type length type in the movie's declaration. In that case, an object relational database management system will intercept attempts to compare values of one type with the other, or to use a value of one type in place of the other. A more powerful form of UDT declaration in SQL is similar to a class declaration in ODL with some distinctions. First, key declarations for a relation with a user-defined type or part of the table definition, not the type of definition. That is, many SQL relations can be declared to have the same UDT but different keys and their constants. Second, in SQL, we do not treat relationships as properties. A relationship can be represented by a separate relation or through references. This form of UDT definition is example. Below figure shows two UDTs, address type and star type. A tuple of type address type has two components whose attributes are street and city. The types of these components are character strings of length 50 and 20 respectively. A tuple of type star type also has two components. The first is attribute name, whose type is a 30 character string, and the second is address, whose type is itself a UDT address type, that is, a tuple with street and city components. Method declarations in UDTs. The declaration of a method resembles the way a function in PSM is introduced. There is no analog of PSM procedures as methods. That is, every method returns a value of some type, while function, declarations and definitions in PSM are combined. A method needs both a declaration, which follows the parenthesized list of attributes in the create type statement, and a separate definition in a create method statement. The actual code for the method need not be PSM, although it could be. For example, the method body could be Java with JDBC used to access the database. A method of declaration looks like a PSM function declaration with the keyword method replacing create function. However, SQL methods typically have no arguments. They are applied to rows just as ODL methods are applied to objects. In the definition of the method, shelf refers to this tuple if necessary. Example: let us extend the definition of the type address type with the method house number that extracts from the street component the portion devoted to the house address. For instance, if the street component were 123 Maple Street, then house number should return 123. Exactly how house number works is not visible in its declaration. The details are left for the definition. We see the keyword method followed by the name of the method and a parenthesized list of its arguments and the types. In this case, there are no arguments, but the parentheses are still needed. Had there been arguments, they would have appeared, followed by the types such as A integer, B character, 5. Method definitions. Separately, we need to define the method. A simple form of method function is, that is, the UDT for which the method is defined is indicated in a for class. The method definition need not be contiguous to a part of the definition of the type to which it belongs. Example: for instance, we could define the method house number from above example. We have omitted the body of the method because accomplishing the intended separation of the string as intended is non-trivial even if a general purpose host language is used. Declaring relations with a UDT. Having declared a type, we may declare one or more relations whose tuples are of the type. The attribute declarations are omitted from the parenthesized list of elements and replaced by a class with OF and the name of the UDT. That is, the alternative form of a create table statement using a UDT is: the parenthesized list of elements can include keys, foreign keys, and tuple-based constraints. Note that all these elements are declared for a particular table, not for the UDT. Thus, there can be several tables with the same UDT as the row type, and these tables can have different constraints and even different keys. If there are no constraints or key declarations desired for the table, then the parentheses are not needed. Example: we could declare movie star to be a relation whose tuples are of type star type by. As a result, table movie star has two attributes, name and address. The first attribute, name, is an ordinary character string, but the second, address, has a type that is itself a UDT, namely the type address type. Attribute name is a key for this relation, so it is not possible to have two tuples with the same name. References. The effect of object identity in object-oriented languages is obtained in SQL through the notion of a reference. A table may have a reference column that serves as the identity for its tuples. This column could be the primary key of the table if there is one, or it could be a column whose values are generated and maintained unique by the database management system. For example, to refer to the tuples of a table with the reference column, an attribute may have its type as a reference to another type. If T is a UDT, then refer T is the type of a reference to a tuple of type T. Further, the reference may be given a scope, which is the name of the relation whose tuples are referred to. Thus, an attribute A, whose values are references to tuples in relation R, where R is a table whose type is the UDT T, would be declared by. Figure: adding a best movie reference to star type. Creating object IDs for tables. In order to refer to rows of a table, such as movies in example, the table needs to have an object ID for its tuples. such a table is said to be referenceable. In a create table statement where the type of the table is a UDT, we may include an element of the form. The attribute name is a name given to the column that will serve as the object ID for tuples. The how generated class can be number 1, system generated, meaning that the database management system is responsible for maintaining a unique value in this column of each tuple, or number 2, derived, meaning that the database management system will use the primary key of the relation to produce unique values for this column. Conclusion. In this chapter, we have covered the following in detail. Introduction to Object Definition Language, that is called ODL. Class declarations. Attributes in ODL. Relationships in ODL. Inverse relationships. Multiplicity of relationships. Methods and types in ODL. Additional ODL concepts. Multi-way relationships in ODL. Subclasses in ODL. Multiple inheritance in ODL. Extends. Declaring keys in ODL. From ODL to relational designs. Object relational model. From relations to object relations. Nested relations. References. Object oriented versus object relational. From ODL introduction to OQL. Features of OQL. Additional forms of OQL expressions. Object assignment and creation in OQL. User defined types in SQL. Operations on object relational data. Ordering relationships on UDTS.